Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will describe practical uses of potential divider circuits. Alright, so I described the use of a potentiometer, which is this device here where you can sort of separate the, or sort of choose how much of the potential of the original EMF you would like to apply to your third resistor. This can always be analyzed like this, and this arrangement is a potential divider circuit. So this device is called a potentiometer. This arrangement is called a potential divider. And we can use those circuits fundamentally to do some super useful things. So without taking into account a particular potentiometer, just for the moment, consider these following circuits. Vin is your EMF, and V2 is going to be understood to be sort of an output potential difference that you're going to do something with. And imagine you're using a couple of useful devices. You can build some interesting circuits. So first, a little bit of quick analysis on the actual physics. If the EMF is equal to I times the total resistance here, the potential difference across the first resistor is I times R1. The potential difference across the second resistor is I times R2. Then the total resistance is R1 plus R2. Then the potential difference across R1 is equal to the EMF times R1 over R1 plus R2. And the potential difference across V2 is the EMF times R2 divided by R1 plus R2. Big picture, right? The idea is V2 ends up being the potential difference in proportion to the ratio of the resistances of these two resistors. Okay, so given that, imagine you insert a thermistor into the circuit. As you might recall, a thermistor has a circuit symbol that looks like this, and a thermistor has its resistance decrease as the temperature increases. In particular, usually there's sort of a critical temperature past which the resistance drastically decreases. This is due to the fact that for these materials, they release additional charge carriers if the temperature is high enough. So those charge carriers sort of pop out of the ionic lattice and decrease the effective resistance. Now, what happens if the temperature increases in this particular circuit? Well, as the temperature increases, the resistance of the thermistor decreases, and as a result, V out decreases. And so past sort of a critical temperature, that V out drops below a certain amount. If you can imagine tying V out to some kind of alarm, this is a way to design a fire alarm, okay? So something that could tell you if the heat has gotten too high. Most fire alarms are actually smoke alarms, so they work in a different sort of way, but this would be a way to alarm something if it went past a particular temperature. Likewise, we can use these guys. This is known as a light-dependent resistor, or LDR. And for a light-dependent resistor, the resistance decreases as the light increases. So as light falls on this light-dependent resistor, that light releases additional charge carriers, and that reduces the resistance. So same kind of explanation as the thermistor. This can be used to create automatic lights. So what happens is you set up this particular circuit, and so as the light that is normally shining upon it during the daytime falls off, the resistance of the LDR increases, and if you tie the potential difference out to a lamp, then you can have a lamp that grows in intensity or really triggers at a particular V out that will turn on when it's dark outside. So this would be an example of a way to set up some automatic lights. So, big picture, potential divider circuits can be used for a bunch of different purposes. There are a couple of examples here that you should take a look at. And in general, you should be prepared to answer questions about this general structure of a circuit. Okay, be prepared to analyze this circuit for different values of R1, R2, and R3. with circuit elements that might vary in resistance at each of these points.